All right, well, before I even reveal what our topic is today, I want to do a little bit of a thought experiment with you to introduce this idea. And it's an idea that I think you'll find to be quite common. So let me introduce it with things you would have learned in even Algebra 1. All right, so go with bunnies. You have 100 bunnies, and after 1 year, they produce 20 additional bunnies. Okay? Everyone have that firmly in mind? 100 bunnies, 1 year, they produce an additional 20 bunnies. Okay? What would you expect if you had 200 bunnies over the course of a year under the same conditions? We would probably expect that there would be 40 bunnies. Very good. 40 additional bunnies. Yes, you might say that for a population of 100 bunnies, that would grow at a rate of 20 bunnies per year. But for a bunny population of 200 bunnies, they will grow at what rate? Yeah, and we want to make sure we're noting here at a rate that's twice as fast, right? 40 bunnies per year for a population of 400 bunnies. All right, now let's turn to another example. Say you have a candle that's 10 inches long, and over the course of, I don't know, burning for, what do you want to say, for a day or something, it burns down 2 inches, say. Now, here's the next candle I want you to consider. A 20-inch candle, how much does it burn in a day? Well, why not 4? Why not 4? What's the difference between the bunny situation and the candle situation? Help me out here, Johnny first. Then.
Every bunny makes another bunny, so the candle is only like the stuff at the top that starts to melt.
Okay.
The entire candle melts.
Yeah, say here with you.
The variable you change doesn't affect the output of the recycling cycle.
Okay. Yeah, the current size of the candle doesn't affect the rate at which. In fact, you can make a bolder claim about the candle. It sounds like it always, fill in the blank, decreases at the same rate, right? It decreases at the constant rate. It doesn't matter how tall the candle is. It always decreases at a rate of 2 inches per day. I don't know, I'm making this stuff up. But yeah, Gabe, do you want to say something too?
Initial condition. It doesn't matter what you see.
Yeah, okay, that's it. Initial condition. I do want to say something about differential equations. Let's try to say, maybe I want to see if you can come up with the differential equation we're going to look at today. So I'll give you, the first one's free, I'll give you the differential equation, the very, very simple differential equation that represents the candle situation. dH dt, how about? Equals -2. You're welcome. Do you hear that? Right? Isn't that the differential equation? And guess what? You know how to solve it too. What is it? What's the solution to that? Yeah, h equals -2t plus c, right? Makes perfect sense in terms of even our Algebra 1 understanding of the situation. Can anyone give me a differential equation that represents the bunny situation? That is, let's call it dp dt. Can you give me something, at least in the direction of a differential equation that represents dp dt? Some expression for that. 20x. Okay. Say more about why you said that.
It's like 20 bunnies per year. It's increasing every year.
What's x? What's x? I had p's and t's. What?
I mean 20p.
20p? Okay, so p, yeah, okay, so that's interesting. So if p is 100, then dp dt is 2,000? Is that the rate at which the bunnies are increasing? We're very, very close though, guys. So her first proposal was dp dt equals 20 p's. I think that's a really nice direction to go in, but I don't know if that's quite right. Because we said over the course of, what was dp dt for if the population was 100 bunnies? Yeah, so what do you want to say instead? dp dt equals 1/5 p. So this is interesting. I think we've discovered this differential equation. Maybe you already know the solution to it also. I don't know. All right, let's begin. We're going to be talking about exponential growth and decay today. The bunny situation, you guys. And I think already you have a very good algebraic kind of pre-calculus notion of what we mean by exponential growth and decay. But we want to just add today, I promise the math today is not going to be super unfamiliar. We just want to add like a calculus lens to your pre-calculus experience with exponential growth and decay. So for example, we have a number of bighorn sheep in a population increases at a rate that is proportional to the number of sheep present. That's exactly what we've just been talking about, guys. Or any population of living creatures, right? Bunnies, for example. Or you have a whole host of other rich applications that we've taught you over the years that exponential growth and decay come into. The value of a car, the depreciation on a house, radioactive elements, etc., right? And we'll cover a couple of those today, and you'll see. I don't know what just happened there. All right, so I'm going to write down the very equation that the two of you suggested, and that's dy dt equals some number, 1/5, say, times y, right? Or we said in our bunny example, dp dt equals k times p. We use p instead of y. But the point is still the same. I hope you see that what that captures is this idea that the rate is proportional to the current population size. Not true for, say, a candle or something else linear, right? In those cases, who cares how much candle there is? But with the exponential growth and decay, as you know, with these kinds of situations, the more bunnies, the more bunny-making power, right? So let's say it again. The rate of change in blue is proportional to, and by proportional to we mean some constant times, the amount present, which remember we have a letter for that still already. It's y in this current context. Okay, so now the next thing I'm going to do is invite you to solve this differential equation. If you haven't already done so, maybe even in your mind. So go ahead and let's go ahead and solve this. I'm trying to, if I have any. And I'm going to ask you, I'll go back to the previous slide for those who need it, but we'll just call y of 0, so we'll solve the initial value problem actually. I want you to solve this differential equation, integrate both sides, all that, and then use just the generic initial condition. If x is 0, y is y0, right? So subject to that initial condition. So that just take a second to solve it with your table and compare answers here. And just kind of verify that the thing you get makes really good sense, maybe, in terms of things you know already. If you think you have an answer, call me over to it. I'd love to see how you're doing on this. Keep in mind here. Or at the very least, if you have a kissing initial condition, where's your seat? What kind of differential equation is this? It's the very simplest time, maybe, that we've been studying in this unit. It's a separable differential equation. So you need to separate, get the y's with the dy, etc. Did you guys get it over here? Yeah, so I think everyone got this, yes? There's a plus C. So you got this. Now some of you are trying to figure out how to deal with the C appropriately. So keep in mind that you can rewrite using properties of exponents, e to the C. And again, why don't we just call that, so this whole plus or minus e to the C thing, after we drop the opposite values, keep in mind that that's another, whether it's positive or negative, that's some other constant, yes? So maybe we call that C2. The point is, I mean, or you can just call it C if you're fine with understanding that it's a different C than the previous line of the work. That's fine too. Just realize that it's all just a constant, you guys. Like, smush it all together. Something. It's some number times e to the kt. Which again, is that what you expected to have happen here? We have some prior knowledge, some prior experiences with this kind of situation where we have a population that's growing in proportion to its current size. We've been doing this since Algebra 1, these exponential models. So when we hear that, we already kind of are expecting, oh yeah, I think the answer is going to be some exponential function as the solution to this differential equation. And the work is not too bad in showing that that is in fact the case. And then applying the initial condition turns out that by C2, really we meant y0, right? So let's just verify that this is the solution. It's in a box now, so I guess I'm sure about it. I don't know. If you plug in 0, do you get y0? Nod your head. And furthermore, can you check it in the original differential equation? If you take the derivative of this, what's y prime, or dy dt? What do you get on the right side? You get y0 e to the kt, that's the derivative, times general, times k. Is that k times the original function that was in the box? Yeah, it is. So we kind of remember how we can check these answers, these differential equations. We can actually make the substitution and check that it works against the original differential equation and the initial conditions that were given. Questions so far? Because now the rest is just kind of like us going back to pre-calc a little bit and like reminding ourselves of things we once learned. The other thing I should say is that from now on, we'll also give you permission to skip all the work. Anytime you see this, and it will be common. It's so common that anytime someone says, consider a population for which dy dt equals k times y, you can just be like, oh, you mean the population that has for its population function y equals y0 e to the kt? You can just say that in one breath if you like. You can also, it doesn't take long to resolve it each time too if you want. But also, we will, in calculus and in the AP test too, we will forgive you if you skip all of this work in the future. Okay? Just good. Just because we kind of have an understanding of how this goes. So you might even put both of these together in a box. This is the exponential differential equation and its solution, you guys. It comes up all the time. And as you know, if k is positive, we get exponential growth, and if k is something negative, we get... Okay, fine. You can change whatever. Do you want to change them both to x's or both to c's?
I'm ready for that.
Okay. You're on your notes, that'll be an x then. Okay. Good. My apologies. Good catch. So you already have, like I said, a wealth of experience with exponential models. For example, you might write one like this in like kind of real world fashion. Maybe you have the amount of something and the initial amount. You have a growth constant, you have elapsed time. So we can start laying into this set of symbols some meaning from the real world if we haven't already been doing that. So I don't mean to bore you with the rest of our time today, but I hope that we're giving you a little more of a calculus flavor on what you've already done in pre-calculus. So the rest will just be us kind of reminding ourselves how this works. Doing a couple problems that you don't feel like there's very much calculus in them. So we're all forgiven. So let's remind ourselves of some of them. Remember this equation? By the way, you can finally prove this limit if you like. Take the limit of this as k goes to infinity. using some calculus knowledge. I don't know that that's the kind of thing I would ask a pre-calculus student to do. And you will arrive at your formula, your number from pre-calc or whenever you learn PEVRT. Radioactive decay, right? Keep in mind that there's this concept of half-life. I'm just doing like a shotgun approach here, right? You remember all these? You remember all this stuff? The one that maybe you have, I don't know how much experience you've had before with this, but Newton's law of cooling is maybe perhaps worth mentioning. Results in an exponential decay function. I think that maybe someone would give you this. I don't know, I mean, they're all just something times something to the power of t, right? Something times t. You do whatever you like. You might copy it down. Yeah, if we have some time, I might come back to Newton's law of cooling too and say a little more about it, because I think there's some rich stuff happening here. The idea, of course, with Newton's law of cooling is that the rate of change of the temperature of an object in surroundings that are a different temperature, the rate of change is proportional to the temperature difference. And so over time, of course, the natural thing that happens, and that is that the temperature of your object, whether it's hotter or colder than the room, approach the temperature of the ambient temperature of the room. So that makes sense. You get this kind of, in fact, just check that that's true. Let's just plug in, we'll talk about it for 1 second here. Plug in a couple of values. If you plug in t equals 0 into Newton's law, into this equation, what do you get? Careful, there's a little bit of work to do. What do you get if you plug in 0 for t? This will all be a 1. And so what do you just get? Thank you. Yes, you'll just get t0, yes? Does that make sense? If you plug in 0 for little t at time 0, it should make sense that you get capital T0, the initial temperature of your object. All right, now the next thing I want you to plug in is 1,000,000 for t. What do you get if you plug in 1,000,000 for t, for little t? Yeah, doesn't this whole term go away then? If this is 1,000,000, we get e to the something obnoxiously large but negative. Well, that's basically, for all intents and purposes, 0, right? So this whole term goes away. And does it approach the ambient temperature, TA, as t grows large? And the answer is yes. So this seems to be doing what we like. There's so much more we could say, but I think that is reasonable for this equation. So there's an example I want to get through, but actually we can come back. I have a nice applet that we can play around with for that as well. But let's play around with this little example as we try to actually put some numbers to these things. And I've tried to pick an example which perhaps hasn't come up in, I don't know, your other pre-calculus experiences. But I know I should have given you like a handout with this on it, but take a second to absorb. This is perfect for you. Posting to a stop here. Imagine this ice skater or something like that. Has a little bit of a physics flavor. We're saying that the velocity is proportional, the change in the velocity, or the acceleration, is proportional to the current velocity. And we want to make sure that that's what we're seeing here, because negative k over m, as fancy as that looks, is just, guys, just a constant, isn't it? So if you want, right away, maybe you can solve the differential equation for v. You can go through the work of actually separating variables, integrating again, and get natural law, do the whole thing again, or you could just say, oh, Mr. Chase told me that I can just write down the solution. That's fine too. So we'll give everyone a second to see what they can write down, what they think the solution is, or re-solve it from scratch. And we'll check the answers here in a minute. And then really B is just kind of an application of, kind of plugging in some numbers to that. A is the calculus part. Think you have a solution, in practice, hopefully, just writing this down. some constant of proportion that is to be determined. M is some constant. We assume, to be fair, and maybe this is wrong, but we assume that your mass isn't changing as you come to a stop or something like that. But maybe it is. Maybe you're like losing rubber on the tire or something, and the mass of the object is changing, and then that would be a completely different question. So some of you are actually resolving it, which is fine. So that's great. All right. For those who are resolving it, you probably need another minute. But for those who just wrote it down, it only took you maybe a couple seconds. So let's have a volunteer, regardless of the method you came up with it. Could you give me a V equation? And if we need to show the work, we'll have someone come up and show the work maybe. But someone tell me what you want to say that V is, or V of t, if you want to call it that. V equals, give me a function, an explicit function in terms of C. I think there should be like an E to the something in it. Doesn't have an equation that works. Okay, go ahead. Okay, and maybe we say like KT over M, or I don't know. Yeah, whatever. The point is just make sure it's mathematically correct. So yeah, very good. Nice job. Can you just, again, just check that she's right? If you plug in 0 for T, do you get V0? Of course you do. And does it satisfy this differential equation? Yeah, the derivative here, dv dt, is equal to the same thing we have here, times negative k over m. So I think I'm convinced. Good. And now the next problem then invites you to plug some actual values in here. So 50 kilograms. That's easy to pray here. That won't change throughout the problem, will it? That'll always be what letter? We didn't come out and say what these letters mean, did we? Or what do you think? What letters should that be? Yeah. I know, this is kind of, like I said, got a physics flavor maybe, but we should have said that maybe up here. By this equation here, we mean m is mass. I think that maybe is the only, and v is velocity, and we should say those things maybe. Okay, so we're giving you an initial velocity here of v0. I think this is your v0. I think this should be your m, like we said. She begins coasting, and her speed 6.66 meters per is 6.66 meters per second after 1 second. So this is v of 1. Do you think that that's enough information for you to solve for the only missing thing? Okay, go ahead and do it, and if you haven't already started. Compare notes. Yeah. Someone have an approximate value for it too? I don't know. 2.490. Someone confirm? Yes. 2.490. bonus points if you can give me the units. It's not immediately obvious, actually. I don't have like a ready. I need to think about it too here. Meters. There are a couple ways we could get in on this. How would you like to do it? I'll go with whatever way of thinking you want to do to get the units here. Do you want to stick units in everywhere we had here and see what happens? Or the other way to do it is to kind of go back to the differential equation. What should K be in order to get an acceleration over here? We could kind of do a unit analysis from the front of the problem too. Which one would you like to do? They should both agree. Let's go back up to the original problem here. On the left we get, what will that be in like? Are we doing meters? Meters per second squared. And on the right we should have velocity, which is meters per second. That's velocity. And mass, which is in kilograms. So what must K be in order to make that happen? What is it? Kilograms per second? Okay, there's the unit analysis. The other way to get in on that, so I think this constant has these very strange units of kilograms per second, which is fine. It's just a constant. It can have whatever units we care to have.
Wait, so is it like she's like her weight's changing? I don't understand.
No, K is just a constant. So I just thought it would be interesting to ask. No, I don't think anyone will ask you that actually in life. Just to be clear, I just thought it would be interesting. Like I said, bonus question. What are the units on that? Yeah, anyone who's done even whatever, chemistry or physics or any of that kind of thing, like anytime we have some constant in an equation, the units are often strange. It's like a unit collector. And so sometimes you get very strange units for the proportional constants in an equation. And we're still working on the same problem here, so see if you can answer those two as well before we head out today. And this will bring us very smoothly to the end of our lesson. Kind of, we're just, if you want to think about it, we're kind of coasting. Thanks, Ash. Just kind of coasting to a stop here, you know, to finish out the lesson. Nice and easy. Weigh in on exponential growth and decay. We'll give you another second to do those, and we'll check answers. Now that you have the full equation. What was it, 2.49? 2.490. It might not be a bad idea to store that value, as you guys all know. So do a little algebra and we'll all... You get the same thing? Ideally you wouldn't use negative 2.490 here. You'd use negative 50 ln 6.66 over 7, or store that as K in your calculator. You've been there, you've done that, you've had this conversation with a math teacher at one point, if not me. Right? Using a stored value here is even more important than in other contexts in mathematics. And the reason is because error compounds exponentially too, right? If you have some rounded number up in an exponent, the error will compound exponentially too. So if you, I don't know, it may not matter very much here. But what'd you get, 39 something and change, depending on how your rounding was?
Good morning, Mr. Montgomery. These are your morning announcements.
I wanted to say something about this one too, but.
I pledge allegiance to the flag of the United States of America and to the republic for which it stands, one nation, under God, indivisible, with liberty and justice for all. Please be seated. Hello, Rockets. Do you like sports, games,
Let's
friendship, or having
get the answer up
discussions
here
about the
during
word and life?
RBC for the last
Come
one.
out to